Hello, everybody. We are going to get started now. Welcome to the webinar, Teaching Statistics to People Who Think They Hate Statistics, Tips for Reducing Statistics Anxiety, with author and University of Kansas Professor Emeritus Dr. Neil J. Salkind. Before we begin, we have a quick poll we'd like you to take. We'd like to know out of which department you teach your statistics course. We'll give you a minute to answer. That poll on the screen in front of you. This kind of information is always helpful to us so that we can know our audience as we go into the presentation. I'll give you another few seconds to answer. Let's go ahead and close that. Okay. Good mix. A lot of education, folks. Always interesting and helpful to know right at the beginning. Okay, let's get started. I am pleased to introduce our speaker today. Dr. Neil J. Salkind received his PhD in Human Development from the University of Maryland, and after teaching for 35 years at the University of Kansas, he remains as a Professor Emeritus in the Department of Educational Psychology, where he continues to collaborate and work with colleagues and students. He has delivered more than 150 professional papers and presentations, and has written more than 100 trade and textbooks, including the best-selling Statistics for People Who Think They Hate Statistics, Tests and Measurements for People Who Think They Hate Tests and Measurement, and Excel Statistics. This one-hour webinar will be recorded and archived for future viewing. We'll be sending out a link to view it and access all the slides to all registrants in the coming weeks. If any of you have any problems with audio or viewing mode during the webinar, please use the Q&A box at the right of your screen, and one of our helpful team members will get back to you ASAP. At the end of the webinar, we'll have some time for Q&A from attendees, so please also use that Q&A box to ask any questions to our speaker throughout the webinar. Please also take note of the webinar hashtag, SageTalks, and feel free to ask questions or leave comments there. In today's discussion, Neil will share tips for reducing statistics anxiety and teaching students how to understand relationships, hypotheses, and significance. Without further ado, it is my pleasure to welcome author Neil Salkind. Welcome, Neil.
Hi, thank you, Susanna, and it's my pleasure to be doing this today. Everybody who teaches this stuff knows that students come in feeling quite anxious for whatever reason. They've heard bad things about the class. They may have even heard bad things about me and you. But I always start off with this very small slide. I'm afraid of math on the left, get over it on the right, and it's called short-term therapy. And the reason I do that is to break the ice. And I think a lot of people get the message that this is material that they can master. And as you may know, I go through lots and lots of different steps in the beginning of the book, suggesting how people might be able to reduce the anxiety that they have. You know, we want to maintain a sufficient, you know that curve, you want to maintain a sufficient amount of anxiety to be motivated to learn, but not so much that it creates problems for them. So some of the things that we do, no joke on the previous cartoon, obviously. It's not meant to be facetious. It's meant to break the ice, as I said before, and give them a little bit of a moment to relax. I do a lot of work with forming study groups. Not only help from study groups, but help form study groups. I ask people where they drive in from if they're driving off campus. I ask people what's a convenient time for them to meet. And we spend about 10 minutes at the end of the first session organizing so that people can conveniently even carpool with others, but nonetheless meet on campus at particular times for the study group stuff, and sometimes I can be even present. And I think that helps also reduce a lot of the fear. And we all know that in these groups, some people dominate and know the information, some people don't, and the smarter students don't need to do that, but so forth and so on. Many of the students who are not that confident, not that experienced, find this to be very useful. I'm always available before and after class for discussion or whatever it is that people might want to talk about regarding the class, the homework problems, the end of chapter problems, and other kinds of issues that might pop up. And I'm always available online. I give them parameters when I'm not going to be available, which is, late in the evening. But for the most part, I'm available during a large part of the day, especially during the hours that I say I'm in the office, and they can also visit, or of course they can email. And finally, I make a note of letting them be cognizant of the fact that lots of people have taken this course, and lots have succeeded. Most have succeeded indeed. I make it easy for them to succeed by testing them using very short multiple choice completion kinds of tests every week, and then a final that's open book. And that seems to, in advance, reduce their anxiety about what's to be done next and so forth and so on. So that's the most effective way that I know of to reduce, to help to reduce the anxiety they have when they come in, and to help at least take the first step in assuring some success on their part. There you can see those delicious ice cream cones. I don't know what they call them in your neighborhood, but they call these little things on them jimmies. Many people call them sprinkles. When I was a kid, they were jimmies. And I want to talk a bit about how I work with correlation. Now, correlations, for me, are taught, the notion of correlation relationships is taught after descriptive statistics, so they already know about averages, and they already know about variability and dispersion and so forth and so on. And so I use as an example the relationship between the consumption of ice cream and the crime level. I'll get to that in a second. But before we do that, I show them lots of different real-life examples of scattergrams, both positive and negative correlations, which I think helps them get the picture, literally, of what things should look like. And I also talk with them at length about the notion of causality versus association, and you guys have gone through this as well. And I talk with them about how things can be shared, and two variables can have something in common, but not necessarily be causally related. And the example that I give for that is the level of ice cream consumption and the level of crime, and I'll get to that in a second. But an important part is also talking about the interpretation of simple correlations, talking about coefficients of determination, coefficients of alienation. But I try and start early with them understanding that a lot of this stuff is interpreted as they see fit. And what I mean by that is according to the rules that they've learned, according to their own, the parameters that they define. So it's not a bad idea, I don't think, to show them visuals like these and ask them to reach some decision about the relationship between two variables. So the first one I show them is on the left, a simple scattergram, and I show them how to locate a data point, 2 on the x-axis and 3 on the y-axis. And there are 10 data points there, and how it's a simple scattergram, just putting up 10 data points. On the right, I show them that's an image of a perfect correlation, where the prediction is perfect, and prediction comes much later in the course, but we can sort of touch on it and just get some idea, what it's about. Then we do the ice cream and crime thing, where the consumption of ice cream increases, as does the increase in crime. And we talk about what kinds of variables or variables might moderate that relationship. And as it turns out, it's no great awareness that it's temperature. As temperature increases, as it goes from 50 degrees towards the end of spring, perhaps into the summertime, people eat more ice cream, and houses are left open, windows are open, people are out and about.
But we want to teach people to trust their intuition and to have some good sense of what it is that they're looking at and what it is that might represent. And that's not only applied in my class to understand the relationships between variables, but it's applied to almost everything else that follows, starting with hypotheses. Now, why do we start with hypotheses? Well, we're talking about now about significance. When I was first started to teach this, and I had my first child asked me, we were talking about ideas and talking about guessing, and she said a hypothesis is an educated guess, and I thought that was a great definition, and it's one that I tended to use. And as you know, there are two types of hypotheses. There are research hypotheses and null hypotheses. And as you can see, null hypotheses are an equality. They talk about a relationship not existing between two variables or two or more variables. It applies to populations, and what's really important is that null hypotheses are always indirectly tested. By the nature of it being a population, by the nature of the rules of inference, we can never fully test the entire population. Otherwise, we wouldn't be interested in inferential statistics, right? We would just describe things and leave it at that. And indeed, lots of people who use statistics in other ways do just that. They have smaller groups of participants. They measure everyone, and there's no inference. When it comes to research hypotheses, we have an inequality, and of course you can have greater than or less than, and that small m is there because everybody and their brother uses everything from an m to an x bar to the word mean, so you get the message. It just means an average score. Well, it means the mean. It expresses a lack of equality. It focuses on samples, and clearly it's tested directly. The whole idea behind having a research hypothesis that you can test directly is that you can infer from those results to the population, which, again, you can't test directly, and you have to test indirectly. That's why I try and make the point. It's a little bit confusing, but I try and hammer it home, that you can never really reject a null hypothesis. All you can do is not accept it. Some people have trouble with that, and that's okay. We just leave it alone. But for the people who don't, they really get the understanding that populations are what we're dealing with or referring to, and we can't test those hypotheses directly. That's why they're called, I think that's why they're called nulls. So the other thing I try and do and make the point, and this is totally facetious and really a lot of fun to talk about, that there's never a 100% chance that something is occurring unless it's occurring. So if the weather guy says there's a 100% chance of rain, it's raining. More importantly than that, there's never a 0 chance of anything happening. Now, I know that's extreme, but if you look at the normal curve, which we'll do in a second, and you look at those extremes, there's a reason why the tails don't touch. The tails don't touch because no matter how small, how remote, and how extreme the likelihood is, there is always a likelihood that something can happen. And I demonstrate that by flipping coins. So we will flip a coin 100 times, and we expect by chance alone for no heads to come up, 0.001% of the time, not 0.001 times. We expect 1/100th to be the probability of one head, 5/100ths to be the probability of two heads. Well, there should be a decimal by the 12 there. 12/100ths for 3 heads. But here's what's cool about doing this exercise. You can show them the likelihood of getting 2, 1, or 0 heads, or 8, 9, or 10 heads if the coin is fair, is 5% or less. It's the perfect example for demonstrating type 1 errors. How the likelihood of rejecting a null hypothesis when it's false, when it's true, and making a mistake is 5%. That is a really terrific way to do it. And you can even have them flip a coin 100 times and note the probabilities associated with each outcome. And we do that sometimes. Most of the time I do it, and sometimes I do it digitally, and so forth and so on. You can, of course, use Excel or SPSS to demonstrate this this phenomena, but it really gets the point across how extreme an outcome one needs to have in order to call the coin not fair, and how there is always a probability associated with any outcome. And we use this cute little distribution of the bell or normal curve to talk about a region for a one-tailed test, and of course if it's a two-tailed test, both regions, where you can not reject the null in light of the research hypothesis, or reject the null, or as I said earlier, you can't accept it. And as you can see, as the values become more extreme, the likelihood of those values occurring is less, but still possible. And those values, of course, as you probably recognize, are the obtained values from whatever statistical test, whatever inferential test you're using, as well as tabled critical values from the back of the book, or however you generate your own, however you generate these values, whether it be by looking up at a table or looking at SPS output or Excel output, or however. Another cool thing that I'd like to do, and I think they're cool, I hope you do as well. Somebody is always bound to ask, what if a variable is not normally distributed? And that's really a great question, and if it's not asked, I raise it. And that leads me to talk about the central limit theorem to them, where, as you know, even for a distribution that's not normal, if you take a sufficient number of samples, a sufficient number of time, and I don't know what sufficient means, it can be 100 or 200 or whatever, you end up with what looks like a flat distribution like this. So I took 50 values, I took 50 samples between the values of 1 and 5, and I plotted them. So there were 16 ones, and there were 9 twos, and there were 10 threes, and so on. And it's a relatively flat distribution. I mean, it's not perfect, but you know that if we increase the random samples to 100 or 200, we would get a flatter line, and eventually the line would be perfectly flat because we would take every possible sample of a specific size an infinite number of times. Okay, so we do that. Then what I do is I take those averages, I take averages of sample size 4, and it can be 5 or 6 or 7 or whatever. So this curve represents 40 samples, and as you can see, there are more samples, excuse me, with an average right around the middle of the distribution than there are in the extremes. And it really drives the point home that if you have a distribution of scores, you have a variable that's not normally distributed by via the central limit theorem, you're going to end up with a distribution that follows the rules, in quotes, of the normal curve. And I think that's really it's really a cool thing to do. I learned this in graduate school in my research methods class, and I still use it. And it always, it's the next best thing to card tricks. It's one of the tricks that seem to drive things really home. So after we finish the central limit theorem, we can talk more about significance and its meaning. We can talk about the true nature of the null, and don't forget we never observe it. It can be true or it can be false. And we can talk about the action that you take, where you accept the null hypothesis, or you reject it, or as I said before, you don't accept it. So you can see in cells 1 and 3, those are correct decisions. The null's true and you accept it, or the null is false and you reject it. And as you may remember, cell 4 becomes a component of power. Cells 2 and 3 represent the types of errors we can make. Cell 2 represents type 1 errors, represented by the Greek letter alpha, and that's the error rate. That's 0.05, 0.01, all of which is by convention, right? There's nothing sacred about 0.05 or 0.01, and now, when you use SPSS or Excel or Minitab or Stata or whatever you use, many of those applications specifies the exact probability associated with a particular outcome. So there's no more P less than, there's only P equal to. I teach it both ways because you never know what's going to pop up in a journal. And of course, in cell 3 is the notion of making a type 2 error and accepting a false null hypothesis, represented by beta. And in cell 4 you can see 1 minus beta is the power. Power is the ability to detect and reject a false null. This chart is about 15 or 20 minutes worth of discussion, and I'll bring it up in subsequent lectures when we talk about specific inferential tests, and especially emphasize the notion of type 1 errors. Okay, then after we talk about those kinds of errors, we talk about significance versus meaningfulness. I think that's critical. There's no such thing as, when we talk about significance, we're talking about statistical significance. Something is significant or not. And I posit the notion that things can be significant, yet they cannot be meaningful. Correlations, for the most part, if you have a large enough sample, correlation of 0.2 or 0.3 is significant when the sample size is 1,000. Now, the amount of variance accounted for in a correlation of 0.3 is 9%. That leaves 81% unaccounted for. Not great explanatory power, and I don't think anybody wants to take that to the bank, but it really makes a lot of sense to talk with them about the meaningfulness of it. And that gets back to the earlier comment I made about eyeballing things, that this stuff is not black and white, that there's interpretation that's most important, and you have to teach people, I think, to understand that. We do that by reading research, reading journal articles, looking at abstracts and looking at article contents and sort of dissecting it, not to a very large extent because my classes are mostly 30, 40, 50 people, but nonetheless I'm teaching them to be able to look at things and be able to make sense out of them. And then we move into the whole notion of actually testing the significance of particular outcomes. We set a null hypothesis, we set alpha, arbitrary, we select the appropriate test statistic, and I have a little algorithm / flowchart to do that. We compute the obtained value, and that's done by carrying out relatively simple algebra, and I urge people to consult the appendix in one of my books that talks about how to do math, or go to one of many different books or online instructional programs, Khan Academy, for example, that talks about simple arithmetic, because that's what we're talking about. We determine the critical value by looking up those values in the book using the tables that are at the end of every stat book. We compare the two, and that's where we come back to that normal curve scene that you saw, slide scene that you saw earlier. If the obtained value is more extreme, the null isn't a satisfactory explanation. If the critical value is greater than the obtained value, then the null is the best explanation. And to finish up, I re-emphasize that you can assign a probability to any event, regardless of whether that event is likely to occur or not. And then I encourage and trust them to use the rules they've learned to make a decision whether or not the outcome is meaningful. And that can be if you're testing a drug that is potentially toxic but can still save a lot of lives, you might be really conservative in the alpha level you set, or quite liberal, depending upon the standards you set, the meaningfulness you suspect the findings could produce, and the rules that you apply, and indeed what you've learned. So I think the most challenging thing is teaching them to think about this whole new way of understanding the way the world works, and that's what brings me a great deal of enjoyment. So now it's your turn.
That was excellent. Thank you so much. Very informative stuff. Okay. Well, now it's time for some Q&A. We are going to spend the next half hour addressing questions from our audience. So audience members, please keep them coming in via the question box to the right of your screen, or if you're using Twitter, go ahead and use the hashtag SageTalks. If we can't get to your question by the end of the hour, Neil has kindly agreed to address them in a follow-up blog post on the Sage blog, Sage Connection. All right, so let's get started here. I imagine that there are people in the audience who are familiar with your books and your writing style, which is very student-friendly and conversational. You also make use of humor in your books. I'm kind of wondering how much of that is reflected in the way you teach, and if you use humor in the classroom.
Yes, that's why I have this brownie recipe at the back of the book as a reward for doing a great job. I just don't. I take this. Let me make an important point. I never use humor at the expense of anyone, or at the expense of. I don't use humor at the expense of anyone in particular. I try and be as self-effacing as I can be, because this is not magic. and I think we all have a lot to learn. And I try and engage them quite immediately. So I use humor a lot, and I always start off with a little bit of a puzzle at the beginning of each session that might be simple mathematical stuff, or a little bit of a crossword puzzle, or a little bit of a joke, but humor. But I do use as much humor as I can, because there are enough serious things we have to deal with in our lives. We don't need this.
Sure, great point. What would you say led you to devote so much of your writing to statistics and research methods?
I read very broadly, about many different topics, both fiction and nonfiction. And I've always been intrigued by the generation of knowledge, creativity, intuition. And I think that research methods and statistics are a great way, although only one way, to understand natural phenomena and the way the world works. So I don't teach it as an end unto itself. As I was taught in graduate school, I teach it as a tool that one can apply to examine findings and outcomes. So I'm kind of the guy that always asks for, is there data about that? You know, do you have any anecdotal reports even? Anything that you can bring to the table that will persuade us one way or the other that a particular direction is the right one to take. And that's generally why I find it so interesting and so valuable, and I want to emphasize as a tool, not as an end unto itself. Many of my colleagues study it as an end unto itself, and that's great. But it's not for me, because of course I was trained as a developmental psychologist, and my areas of interest were outside of strictly statistics as anything other than a very effective, cool tool to use.
Okay, excellent. We have a question from one of our audience members that you may be able to speak to. Can you give some suggestions about how to build a sense of community if one's teaching a course online to students who may be from different places across the country? Do you have any experience with that?
You know, in all fairness and honesty, I don't. I get questions from students all the time electronically, and I answer them. But the only way I would have to think about that. I have never had that experience, and so I apologize for not being able to suggest anything.
Okay, fair enough. I have another question here. In your experience teaching statistics, do you find that there are pieces that are most challenging for students to understand, like consistent topic areas that trip a student up?
Okay, well, besides the simple calculations, which people make mistakes, for example, a student the other day wrote to me and said, I've been doing the prediction stuff and I can't get it to work. I keep coming up with these values. And the problem was that they were predicting X from Y rather than Y from X. So that was part of the problem, just understanding what the equations say. When I think about it, probably the most challenging thing is understanding the notion of significance and what error rates represent. So we go over that every week for probably the last 2/3 of the course, because we're starting to talk about inferential statistics. So hopefully through different examples and through repetition and through explaining it any way that I can or asking someone else to help, it becomes more clear and they can understand it. And as I said before, I have a quiz every week, and that gives us another chance to review the previous week's work after I ask them if there are any questions, and also to be able to tie that together with the current week's work.
Okay, thank you. All right, we have a lot of questions coming in from the audience. Let's try to move quickly through them. How do you address on the first day of an elementary statistics class when students tell you that math has never been their strong subject?
Well, you could be facetious and say get over it, which is not necessarily fair. and you can tell that joke, which, you can put that up on the board, which isn't going to make them any less anxious. I tell them that I have at times had a separate session going through an appendix from one of my books or another book on simple mathematical or arithmetic manipulation, which starting out with very easy questions, and also I take off when I grade papers. I take very little off for not getting the correct answer if it's a mathematical error or arithmetic error. I take out much more if it's an error that indicates they don't understand the material. So I tell them that, and they get that. They get the message that what's important here is to understand ideas, not be able to solve equations, although the best students are going to be able to solve those. It is interesting that some students find the arithmetic to be quite simple, and others don't have the background and don't have the aptitude, perhaps, or the ability. And like I said, I try and introduce that early on, show them how that can be done, ask them to stay afterwards when we practice things, and in general, maybe even talk about why they feel that way about arithmetic or mathematics. Some of them feel that way because they have kids that are whizzes, and they aren't, and they feel kind of like embarrassed by it. But we try and get over it as best that we can. Everybody has a different reason for why they find math to be something that's uncomfortable for them. But I really work hard at convincing them that all it is, addition, subtraction, division, and multiplication, and you just have to go slowly and be careful and practice. I hope that it helps you.
Yeah, I think that's a great answer. And actually, kind of along those lines, what about those students who say that statistics has nothing to do with their lives and they're only taking the class because it's required? Do you have a specific approach with those sorts of students?
Well, I sort of don't have a lot of sympathy for them. I mean, like, I didn't put them in the class. My job is to teach them as best I can. If they don't think it's worthwhile, they should discuss that with their advisor. I think we can point out very effectively, and I do this at times, the headlines in the paper, whether it be research reports about research that's going on in health and other kinds of well-being, or politics, or take a look at what happened with the polling and measurement error. I mean, that's astonishingly relevant to what happens in our world. But I don't spend a lot of time on convincing people why they should be here, because I didn't put them there, and my students are there because they want to be. So, it's kind of like their responsibility. I take that pretty seriously, that they're there because it's something worthwhile. It's not my job. I think it's worthwhile. It's not my job to prove to them that it is. It's a difficult situation to be in, but I think it runs into the whole thing of I am not anything. I am your teacher, and I will teach you this. If you find it of value, great. If you don't, there's not a whole lot I can do. You can teach people to understand, you can explain things to people, but you can't necessarily teach them to appreciate it.
Yeah, it's funny that you just mentioned.
Uh-oh.
Oh, I'm so sorry. I was on mute.
Okay.
Yeah, you just mentioned polling and the election, and we've gotten some questions on that, and just kind of your thoughts and your insights on what may have happened with the polling errors.
Oh, I would take articles from newspapers and from the internet where the pollsters talk about why they made the mistakes they made, and you can just exploit that no end in terms of understanding the principles of basic statistics. They all sample, they all infer to a population, they all come up, they all conjecture as to what their conclusions will be, why they'll be that, and so forth and so on. And I read one the other day, and this pollster gave 10 reasons why she was wrong, and 8 of them were directly relevant to the stuff we talked about today. So I think you could do a terrific job on that.
Okay, thanks. What recommendations do you have for dealing with students who can produce the correct answer on a test or in the homework, but appear not to understand the concept behind it?
Well, what I do is my test items and my practice items are by far more based on concepts than they are on execution of computation. So I want to be sure that they know how to compute a t-value, and I want to be sure they know how to use an Excel function or SPSS to compute an obtained value for a t-test. But I want to also make sure that they understand what that obtained value represents, how it's compared to a critical value, and what the outcomes might be. I can only guess. That's the only way I can know they don't understand the concepts, and that's the only way I can emphasize why concepts are very important to understand. The figuring out of the math is just kind of an ancillary notion. I mean, we go through it a lot. We spend a lot of time on it, but we spend a lot of time interpreting outcomes. Hopefully, them trusting their intuition and their decisions they make given data. So it goes hand in hand. I rarely run into students that can produce an outcome and don't have some understanding of the concepts, but I certainly can understand how it can happen, and I certainly emphasize understanding those concepts after they're finished computing the values. Done.
Thanks. You touched on this a little bit earlier, but would you mind sharing some of your strategies for making statistics more applied to students?
Yeah, sure. One of the things I have them do throughout the course of the semester is everybody, since this is a service course, as this for many of us, so there are people from all different fields, I have them select a journal article that uses some kind of, statistical reasoning, and to share that in a small group with the rest of the class, and of course the journal articles in their field. Now you can ask the question, if they don't find it relevant, then what can you do? I mean, it's their field. If they don't find it relevant, it's all the worse for them. But most of them do. Most of them report on it, and I show them how to report on it the week before it's due in terms of what we go over abstracts and talk about what they might say and talk about how to read them. And through your education you've gotten much better at reading abstracts. Well, they do as well. So people can bring the first page of the article to their group, to their small group of 5 or 7 people, but also reproduce it for everybody in the group, and even better, give it out the week before. People have time to read it, and the person who's reporting on it can spend no more than 10 minutes talking about the outcomes, why it's relevant, what questions can be raised, and so forth and so on. It also gives the opportunity, when we all get together again, for them to ask questions to me or other people in the class about why this is the way it is, and so forth and so on. That happened when p-values started to become more exact, like p equals 0.043 versus p is less than 0.05. Why is that? And the whole class learned about it. So that was one strategy that I used to make stuff much more applied. And I'm always asking people to use examples in their own discipline. And for the most part, they can do it because they're interested in what they're learning or what they're doing. And it works. It seems to work. Done.
Okay. We have a question from an instructor regarding distribution tables. This person wants to know, is it necessary for students to know how to use them? Some of this person's colleagues say that it's old school and that they should teach their students how to use a TI-83 or 84 calculator instead. Do you have any thoughts on that?
Yeah, and that's a great question. And that's one I always think about when I teach. So I teach 2 ways of doing everything. One is manually, and maybe I'm trying to get back at them because I had to do it manually using a Monroe mechanical calculator, because there weren't computers when I was in graduate school, at least personal computers. And then I teach them how to do it using Excel or SPSS or whatever application is handy. The reason why I have them do it manually is because I talk about what the formula represents. And I talk about, for the most part, the numerator being the differences between parameters and the denominator being an error term. And when we go to the tables, we can see how values increase or decrease depending upon the degrees of freedom and how they're distributed. So I think doing it manually really teaches something, especially, like look at analysis of the variance. It's that fraction of between sources of variance divided by within sources of variance is such a clear example of how when distributions differ increasingly so, the error term, as distributions get further apart in their values, the error term becomes less or stays the same, the obtained value becomes greater, and you can see that as you go through the different distribution charts or significance or obtained values in the different tables. I can understand why people just use a calculator to compute a p-value, but I kind of like to do it manually. And of course, since we all know that the human race is doomed, they'll only be using distribution tables. Computers won't be available. I'm only kidding about that. But I think it's a very worthwhile exercise, and it is old school, and, there's nothing wrong with old school sometimes.
Well, hey, on the subject of not using computers, we got another question, which I'll just read from the person who submitted it. As a doctoral student, I am wondering how you feel about teaching stats in a computer lab with SPSS or in a classroom without it in the traditional sense. I am in a program that does not use computers or SPSS for its stats class and wondering the pros and cons of the circumstances.
Wow. Well, given the modern world, and given that we're training people to have skills that can be applied outside of school when they graduate, I think it's a bit remiss not to offer students the opportunity to learn this using tools such as SPSS. I understand there might be facilities constraints. On the other hand, you can never go wrong teaching this stuff without using computers, because the computer stuff is pretty easy to grasp once you have the basic concepts. Having the computers doesn't teach much about using a computer, using Excel, SPSS, Minitab, or whatever you want to use, doesn't teach much about the notion of what it is that you're doing. While on the other hand, the jump from learning about this stuff without the use of a digital technology is a small jump to the use of digital technology. So I combine the two, but I have the pleasure of having a classroom that's pretty well equipped. And I can't see how in these circumstances that one can do one without doing the other, but if I had a choice, it surely would be teaching material without computers and then letting students fend for themselves using computers.
Okay, thanks. I am wondering about classroom activities. Do you have suggestions for any activities that other people could use that would get their students up and moving around, teaching inferential concepts like correlation and ANOVA?
You mean physically getting up and moving around?
Possibly.
Okay, well, I have them form groups. And that means getting up and walking around and getting into the new groups. And sometimes the groups are their friends or their buddies, or sometimes they're randomly assigned groups. I tend to not keep the same groups because it helps keep things a little bit fresh. And I tend to go over some of the homework problems. I tend to go over the problems at the end of the chapter. Now, that's in the book that I use, and those are the kinds of problems that I put forth, maybe changing some values and switching them around a little bit so they don't do exactly the same thing they might have done for practice at home. But all of those tend to have some degree of application that they find useful, and it seems to work out. It seems to work out pretty well. Other activities include what I talked about before: the notion of understanding inference as a function of the articles that they read, looking at headlines and making decisions about, what steps one would take given certain amounts of information. Everybody knowing that we have to often ask questions about, does something work, and do we have any empirical data that we can use to reach a conclusion? So, those are some of the activities. They're as hands-on as I can make them, and I'm always looking for new ones.
Okay, thanks. What do you think about the statistical reform, and how should it be presented to students?
I'm sorry, the statistical what?
The statistical reform. Are you familiar with that concept?
No, I am not. Are you?
Huh. No, I can't say I've heard of it. I'm pitching it without being familiar myself. If that person who submitted that question might want to elaborate in the chat box,
Great.
please feel free to do so, and we'll get back to that
Please clarify.
a little bit later. Yeah. Okay, how about another question? How do you answer the question, what are the degrees of freedom?
Oh, that's really hard to do, and I've never been entirely successful. There's the book definition, of course. I just tell them that it is very similar to the number of groups or the number of participants in a sample. That's sort of a cop-out because it doesn't really explain that, although you can talk about degrees, or you can go on and talk about it as I do, in that degrees of freedom is the amount of room that's left to wobble given certain constraints by the problem that you're trying to solve. So if the degrees of freedom are n-1 and n is 30, you know there are 29 degrees of freedom. There's relatively little wiggle room. If you have a larger sample, there's even less because you have that large sample which represents a larger portion of the population. I have never been able to find a satisfactory way to explain that. And so I always default being that it reflects the number of groups, the number of participants in a sample, and the amount of room that's left to wiggle, wobble, or whatever you want to say, given the constraints that are placed upon you by the empirical data.
Okay. We just got a question that reads, you used to have crosswords to teach statistical terminology to ease math anxiety. Did you find a better alternative?
I didn't get that one word. Better alternative to what?
Crosswords.
Oh. Well, you know, there's a wonderful Google aptitude test where you put a 1 on the board, and then underneath it you put 2 1s, and then you put underneath that no, you put a 1 on the board, and you put, that's right, underneath it 1 1, then you put 2 1, then you put 1 2 1 1, and you ask them what the next line is. Well, it's not mathematical. It's 1 1, 1 number 1, or 1 number 2, then 2 numbers 1, or 2 number 1s. So it's those kinds of puzzles I look for that kind of get people in the mood to think a little bit out of the box and have a little bit of fun doing it. The crossword puzzle stuff is just fun. I don't have a lot of alternatives. I'll ask them what the Coriolis effect is, and that has to do with the rotation of the Earth and the way water goes down the drain. Or I'll ask them a question about some somewhat esoteric science thing that's popped up in the news, or a political thing, or a food thing. Like I used to ask, you know, we talk about sampling, we talk about stratas, right? You talk about different layers of sampling, and that's what stratified sampling is all about. Well, somehow we always talk a little bit about cooking lasagna, and then you don't have to cook the noodles. You can really just put the noodles in stiff, and with sufficient sauce, they'll cook in the oven. So, I mean, like, you know, it's all what your preference is. I kind of have fun doing that stuff, and people tend to enjoy it, and it doesn't take more than 5 or 10 minutes out of a 3-hour period, or 5 minutes out of a 50-minute lecture, and it seems to pique their enjoyment.
Okay, great. I have a follow-up question to that inquiry about statistical reform from the individual who submitted that question earlier, and they have provided some clarifying information, so I'll read that now. The person clarified statistical reform is putting less emphasis on p-values and significance to move towards effect sizes, confidence interval, and meta-analysis. Do you have any thoughts about that, Neil?
Oh, absolutely. And effect size, absolutely. Effect size is something that I introduce after the first the inferential test that we do. And I talk about the difference between I talk about the importance of significance, the importance of meaningfulness, and the use of effect size. And that seems to be easy to understand and very relevant. And in fact, if that's what statistical reform is, then I'm a reformist, because I emphasize much more the value of interpreting stuff rather than just simple significance values. As far as the meta-analysis, that's a little bit ahead of the groups that I teach, although I do introduce it towards the end of the course and talk about what it means, what it represents, and I give them an overview with an article and show them how it's done, but nothing more than that. But I think it's a great question. Thanks for clarifying that for me so I'll understand it next time.
Yes, I echo those thank yous to that individual who clarified. We have just about 5 minutes left, so time for a couple more questions. Again, Neil has kindly offered to answer any questions that we did not get to, so we will later. For right now, here's a question. For a person who has a more qualitative background, how would you suggest that they approach building up their quantitative skills? Do you think that that would be an opportunity to self-teach, or would you have any recommendations on how a person could build those quantitative and statistical skills?
Well, this might be an old school response, but I believe that everybody should have as many tools in their box as they can. So my students, my graduate students in particular, always take a qualitative analysis class as well as quantitative analysis classes. Everybody has a philosophical bias. I think both are very important, and I think it's even more important to understand that certain questions require certain tools to answer them. The tools should not dictate the questions that we ask. The tools should allow us to help us in answering those questions. But if you are a quantitative methodologist, if you're a qualitative methodologist, I think you owe it to yourself to take a quantitative class, if not more than one. I have colleagues, close friends and professional colleagues, who are world-renowned in their content area, who deal with N of 1 studies. They deal with one subject, but they fully understand what analysis of variance is about and what factor analysis is about and how they're used. And I can't think of any reason why anybody should not be fully versed. Doesn't mean you have to embrace the philosophy underlying those tools. It doesn't mean you have to use them or engage in them, but I think you do have to understand what they mean and how they're used. I think you owe it to yourself and to your students.
Great answer. All right, one final question for our talk together. Direct from the audience. One of my colleagues learned to meditate in her stats class. Is this common?
Well, actually, we meditate for half of every class. Only kidding. You know what? Who am I to judge, right? If that works for them and they learn the material, I think it's great. I've never heard of it before, but I think it's great. As long as they chant when they meditate, because meditating without chanting is like nowhere.
Yeah, what do you think they're chanting in the stats class?
I'm sure they're chanting the definition of a type 1 error. You know, what else are you going to chant?
Well, that's great. Okay, I think that's a perfect note to leave it on. Once again, everyone, thank you so much for sending in your questions. We will get to them later. Neil, thank you so much for this great presentation. We really appreciated it.
For sure.
Thank you so much. Okay, everybody. Just to wrap things up real quick, if you are an instructor and you're considering one of Neil's books in your course, feel free to request a complimentary copy at sagepub.com. If you're not an instructor but you think you may be interested in purchasing one of his books, we'll be sending out a follow-up email with information on how you can purchase one of his books at a 20% discount. So look for that in the coming weeks. And again, thank you everybody for joining us. Thank you for the questions. Special thank you to Neil, of course. As I just mentioned, please be on the lookout for that email that will include a link to view this entire webinar as well as the slides and answers to questions that we didn't have time to get through today. Please stay connected with us on the blog, Sage Connection, and on Twitter at @sage_methods for more information on upcoming webinars. Thank you so much, everybody. Have a great day.